So welcome, everybody. I'm Bob Carter. I'm Deputy Director at National Institute of Arthritis, Musculoskeletal, and Skin Diseases, and have been with AMP since the conception back as Francis described it. So in the beginning was the Heaver meeting that Francis described. What he didn't quite talk about was it wasn't just genetics. It was that there was a lot of late-stage failures in drug development at that point. More than half of stage 3 clinical trials, phase 3 clinical trials failed, and most of those failed because of lack of efficacy. That's pretty stunning, saying we really don't know what we're doing. So at that point, Francis was, as you all know, all about genetics. And we also sort of, when he came back and said he had this meeting and he thought we could really do target validation, he thought we were doing genetics, and that's what we all sort of assumed. But he did do the thing with the Boston Consulting Group that he and David described, where they talked about disease deconstruction, of understanding what's happening in the tissues. And so of the ones that were nominated, one was autoimmunity. And when the question was raised, well, who wants to do an AMP in autoimmunity? The way Steve Katz said was that everybody else stepped back. It wasn't that he stepped forward, it was that the only ones left standing. So that fell to NIAMS to try to organize something. And Steve came and said, well, what are we going to do? Do you have any ideas? Well, yes. The good news is that genetics at that point had identified, now over 100 different loci that are risk factors for, say, rheumatoid arthritis or lupus. But the problem is at that point we had no idea what they were doing. There was no way to tell what the genes were doing in the diseases outside of the blood. And most of these, the risk loci were expression controlling. They weren't coding. But we couldn't look at where they were being expressed causing the disease. So the idea was to try to get tissue to understand the gene expression of these different risk loci. And that's where we started from. And the good news was that investigators in Europe were pioneering the use of ultrasound-guided biopsies to get synovium with patients with RA. So David Woolley, bless his heart, wherever he is, helped organize this meeting up in Boston that was the best meeting I've ever been to. And we got Mike Brenner to be the co-chair because we knew of his dedication to studying cells in the synovium. And at that meeting, he brought Nir Hakonen, who was working at MIT to help develop the single-cell transcriptomic platforms, which at that point were pretty crude, but at least they were you could see that this was going to be emerging technology. So what happened at that meeting, it was the most fantastic meeting of industry, nonprofits, and NIH have ever seen, and academics, and you could see the light bulbs go off. Yes, we can get tissue. Yes, we can actually look at the cells in the tissue. Wouldn't that change the whole approach to understanding not just the risk loci and how they were being expressed, but the targets that we want to use to try to treat the disease so we don't have these late-stage failures? And that really was where it started. And I cannot tell you how much I appreciate the work of so many who went into this, and all the investigators, the people who ran the different awards, the steering committee who worked so hard through actually some fairly tough times, and the overall executive committee, which provided the leadership for this whole thing to happen. And it is true that innovation happens in small groups. Like the development of single-cell technologies often happen in small groups. But what NIH can do is bring people together to make connections. And that's exactly what happened here. We brought together the clinicians, together with the scientists who are developing the single-cell transcriptomics, and got help from the EU in bringing biopsies to this side of the Atlantic. And basically, the rest is history, and that's what you'll hear about. But having those people come together, and now we understand the cells that are involved in the synovium in rheumatoid arthritis, in the kidney in patients with lupus. That's an unbelievable statement compared to where we were just a few years ago. So thank you to all, and I have to say, starting with that meeting in Boston and ever since, with a few blood, sweat, tears on the way, this has been the thrill of a lifetime. Judith.
Well, thank you very much, Bob. And so I'm Judith James. I am at the Oklahoma Medical Research Foundation, and I'm just going to give you a few kind of overarching themes for AMP-RA lupus and AMP-AIM. So why have an AMP in arthritis, autoimmune, and immune-mediated diseases? Because arthritis, when you think of them collectively, are the #1 cause of disability in the United States, and many of our forms of arthritis have no FDA-approved drugs for treatment. In addition, autoimmune diseases afflict 1 in 8 to 1 in 10 U.S. women at some point in their lifespan, and depending on how many autoimmune diseases you put into that trench. And so the other thing to remember is that even though we're making strides, even though we're improving, lupus still remains a top 10 medical cause of death of women, especially women between 15 and 45 years of age, and that's a top 5 cause of death in women of color. And so I think the most striking thing that I just want to make sure everyone who doesn't think about autoimmunity all the time has in the back of their mind is that we're seeing a significant increase in the number of people who have autoantibodies in their peripheral blood. And so based upon a study out of NIEHS, we've seen a 50% increase over the last 30 years, but that's a 300% increase in teenagers. And so these are diseases that are difficult to diagnose. Their treatments are many times toxic and not directed, and currently they're impossible to cure. And so that kind of set the stage for why we thought that the aims and goals of the AMP-RA lupus program should really focus on this. And you've heard the word deconstruct, deconvolute. And basically we wanted to tease apart what was happening in the joint, what was happening in the kidney, in rheumatoid arthritis and in lupus. We wanted to be able to define shared and disease-specific biologic pathways to help with new targets, but also to help with improved identification of subgroups of patients, like we just heard about in AD, so that we could see prognosis and response to therapy, as well as to start thinking about these diseases from a systems-level understanding and to establish the unique and novel infrastructure that we need to basically do transdisciplinary integrated team science to address these important, impactful diseases. And as one of our colleagues up here said, I think every meeting we ever had, the bottom line was, tissue is the issue. And so the RA lupus program basically had 3 different phases. You're going to see a lot of data from phase 1 and phase 2. And you're going to see clinical data as well as data mainly looking at single cell experiences. And so these are the acknowledgements for AMP-RA in lupus. And so you've heard that NIAMS was one of the champions for this. NIAID also made significant contributions, as well as many of our funding partners, both from pharma as well as our patient advocacy groups. And then we had many different network sites, many different individuals that are on here. Hundreds of people were part of AMP-RA lupus. And so, but when we started coming to the end of AMP-RA lupus, we realized that there was still so much that we needed to know. And so AMP-RA and lupus really focused more on later stage disease in patients who didn't respond or didn't respond optimally to therapy. And so we wanted, with this new vision, to not just think about RA and lupus, but to add other autoimmune diseases that shared either the target organs or some common molecular mechanisms. And so we were very excited to see that Sjogren's disease was added to this list, because Sjogren's is the 2nd most common autoimmune rheumatic disease, and based on a new study out of the UK, may be one of the fastest growing. It targets the joints, just like we see in all of these diseases, but it also targets the salivary glands and lacrimal glands. And then we also wanted to add psoriasis, or psoriatic spectrum disorder, because we could compare and contrast the skin from lupus with psoriasis. And so this just reminds me to encourage everybody to come to the posters, because we have lots of additional data about the background, but this is kind of our one slide that says it all for what we want to do in AMP-AIM, which is to basically bring together all these different types of technologies to integrate tissue and blood information to identify shared and unique determinants of early disease. This is our framework to do that, which includes this trans disease project that really focuses on early disease across the 4 different diseases, but also to study the same tissue, or skin or synovium, in at least 2 different diseases, and then, of course, to have some disease-specific projects as well. And these are the different protocols. We thought it was kind of challenging with 2 or 3 the first time we did AMP-RA lupus, so now we have 12, just because AMP is a very ambitious organization, right? And so you'll see that many of these have to do with early disease and with non-response to therapy. And then I'd just like to end my part with the Team Science Leadership Scholars Program. So this was a unique opportunity. One of the things that clearly came out in our AMP, and I'm sure with many of your others, was that not only was this great to generate data to make new novel insights, but we also see the launch of individual careers of fellows and junior faculty for people who were trainees who now were able to leverage infrastructure to be able to launch their independent careers much faster than normal. And so this basically turned into something from the Office of Research in Women's Health in collaboration with NIAMS and the Office of Data Science Strategy with the champion of Susanna Surratt-Stein and Lisa Begg to basically identify women, to identify scientists who are focused on women's health and to build team science skills. And these are 6 scholars, everything from pediatric rheumatology to computational biology, and we have a second announcement that's currently active, and you can go to ampaim.omrf.org. And we also have had pain supplements in the Opportunity Fund. So with that, I will close, and we will bring up Anna Greenwood, who you've already seen once today, but she'll talk about autoimmune disease.
Great. So I'm going to talk about SAGE's efforts on the data coordination for AMP-RA SLE and more recently AMP-AIM. And so, as you heard from Judith, autoimmune diseases are a very common cause of devastating disease in a growing population, especially in women. But many of these can individually be considered a rare disease because of their unique kind of low prevalence rates. And I would say data sharing and aggregation are really exceedingly important for these rare diseases where there are few patients of any one specific disease, and tissue is the issue, tissue samples are low and data volumes are rare. And so bringing those together in a central repository is really valuable for the research community and fundamentally patients as well. I won't belabor this. You heard from Judith about the goals of the AMP-RA lupus and AMP-AIM projects. But underpinning both of these stages of the AMP-AIM project is data sharing. Similar to all the other AMPs, and you'll hear the same theme throughout these 2 days, data sharing with the broader community within the consortium and then with the broader research community is of high importance. Here is a snapshot of the data that is currently either available or planned to be generated through these 2 projects, both AMP-RA lupus phase 1 and 2, and then now in AMP-AIM, which is an expansion of diseases and modalities. Initially, the data was shared through the import platform, which is an NIAID platform, and I understand that the CyTOF data generated through this was one of the most highly accessed data sets from this entire portal, sort of showing again the power of resharing data and allowing the community to use that. But going into AMP-AIM, the consortium had a broader goal for coordinating data both within the consortium and beyond. And so the 3 main goals were to, 1, leverage the systems and processes that were already in use for another AMP program, in this case AMP-AD, and that's why I'm talking about this. And then also to enable collaborative analysis by the consortium members prior to public data release to do some of that harmonization work that we talked about for AMP-80 that's been done similarly in AMP-RA lupus as well. And then finally to create a community repository dedicated to autoimmune diseases so that they could kind of start to nucleate a community. And we have, at Sage, we have experience with data coordination, not only for big projects like AMP-80, but also for rare disease. And so I just briefly wanted to highlight this neurofibromatosis resource and just our experience with bringing together a community of patient advocates all the way through to researchers, and sort of seeing what happens when you bring when you develop a data resource and start to nucleate a community. And so we were looking forward to doing this same thing with the AMP-AIM project. And so we have developed this architecture now where the teams that you heard about from Judith are generating and contributing data into our Synapse platform where the consortium can analyze this and do that critical harmonization work. And then this is shared with the broader community through a new portal that we've developed called the ARC, or Autoimmune and Related Disease Knowledge Portal, where external investigators can get access to this. And this is just the homepage of the ARC portal, which was launched about a year ago in December 2022. And all of the SAGE portals, including the 80 Knowledge portal that you heard about, use a pretty simple way to help navigate the portal to find data and resources. We organize things in a hierarchy of information that you can access using the Explore menu, and then you can browse and filter to find the resources of interest. You can also access the RA lupus data from data sets that are curated, or also just by looking at all the data files and which disease they're associated with. And as we're looking forward to the next several years of this program, we're going to be updating the ARC portal by, of course, incorporating the new data and an additional set of annotations to make the data more discoverable. We're going to be adding an ability to explore the publications and how those are linked to the underlying data, the ability to find data by participants, and then adding any computational tools that have been developed as well. And just very quickly, wanted to thank some of the SAGE team who isn't here today for the ARC portal, but I think that's it. Thanks.
Hello, I'm Michael Brenner, and it's my pleasure to talk to you about rheumatoid arthritis. The RASLE consortium undertook a single-cell disease deconstruction of rheumatoid arthritis by focusing on the synovium. And as shown at the left top corner, we got synovial biopsies, a total of about 80 biopsies, and subjected them to extensive analyses. I'll talk just about two types of data today. Along the top, the red arrow points to a main pipeline in which the disaggregated cells were then ultimately captured to get both an mRNA library and a site-seq protein library. And then down along the diagonal is a pipeline where we obtain T-cell receptor and B-cell receptor repertoire data. This is a UMAP from the RNA-seq data of the synovial samples, the CD4 cells to the left, the CD8 cells to the right. Now, when we came into this, based on decades of research, we and others thought that RA was a Th1 disease or a Th17 disease. However, the single-cell data did not support either of these ideas. There's, of course, a lot of interferon gamma-producing cells, but most of them were CD8 cells and NK cells. We found very few Th17 cells. Instead, the main finding in the CD4 compartment were of TPH, or T peripheral helper cells, that drive B-cell differentiation in synovial tissue. And to bring some of the Atlas information alive, I'm going to reference a number of mechanistic papers along the way that were developed out of this. One from Deepak Rao in my laboratory examined these TPH cells and showed that in the synovium they associate with B cells, where through CXCL13 and IL-21, they drive B-cell differentiation. The important point being it's in the tissue, not in the secondary lymphoid organs like lymph nodes. Looking at the CD8 T cell side, the surprising finding is that the predominant CD8 tissue phenotype was of a granzyme K CD8 T cell, something not much is known about. A mechanistic paper from Helena Johnson and Fan Zhang, and a collaboration between the Ray Xiaojuri lab and my lab, is defining what these cells are, and many laboratories are now figuring out what granzyme K does to drive inflammation. This is the UMAP on the B cell side. As you can see for the clusters highlighted in red, there were ABCs, those are age-associated B cells, widely considered to be pre-plasmablasts, and GC, or germinal center-like B cells. What this suggested is that these populations might be differentiating into plasma cells in the tissue, and this is supported by the large number of plasmablasts and plasma cells to the left of the UMAP. Two mechanistic papers which really support this idea. One came from Jen Anilich's lab, where she described NR4A1, 2, and 3 positive B cells that are implicated in mediating ectopic lymphoid structure development because they produce lymphotoxin alpha and IL-6. And the B cell receptor repertoire analysis carried out in the laboratories of McDavid, Rao, and Anilic showed clonal sharing in the B cell receptors between many of the activated B cells and the plasma cells in the tissue. Again, then, as the title of the slide suggests, this implicates ectopic lymphoid structure formation and extrafollicular B cell differentiation from the ABCs and the TP8 cells happening in the synovium itself, as opposed to or in addition to what happens in secondary lymphoid organs. Another major finding to come out of the RA work is the ability to stratify RA patients based on the cell type abundances found in their synovial reactions. These are shown here as what we called CTAPs. Many of them were enriched in T cells. You see TB, TM, and TF, reflecting the samples that were enriched in T cells and B cells, or T cells and myeloid cells, or T cells and fibroblasts. While other samples were mainly myeloid cell dominant, or still other samples were mainly composed of stromal populations of fibroblasts, the F-CTAP, or endothelial cells and fibroblasts, EFM. I'll show you how these CTAPs may be very important in understanding the disease. As we looked at the myeloid cells, the UMAP shown here on the left, we found multiple subsets of tissue-resident macrophages. They were characterized by phagocytic receptors like MER-TK, mannose receptor, highlighted here. In addition, there were also several clusters of highly inflammatory blood monocyte-derived macrophages, producing IL-1 beta, showing a strong interferon signature with STAT1, or expressing osteopontin. The reason these different subsets are important, if you now look at the CTAPs, here osteoarthritis, EFM, and the fibroblast CTAP are mainly composed of the MER-TK relatively non-inflammatory tissue-resident macrophages, more involved in debris cleanup and resolving inflammation. In contrast to that, the M and TM, the myeloid-dominated CTAPs, were composed of the highly inflammatory macrophages. So if you can imagine, if you're developing a drug against inflammatory macrophages, you want to treat the patients with the CTAPs to the right, not those to the left. A mechanistic paper that was very informative came from Laura Donlin at HSS, where she described a highly inflammatory population of macrophages that produced HBEGF, heparin-binding EGF, that transactivated fibroblasts to make them invasive. And speaking of fibroblasts, here from AMP phase 1, we defined fibroblast heterogeneity, as shown in the TISNE map to the left, as 4 major fibroblast populations. And the population with the red circle around it is important because it was highly expanded and represented highly inflammatory fibroblasts, making most of the IL-6. Interesting work carried out by Kevin Way and Ilya Korsunsky, again in the Ray Xiaojuri lab and my laboratory, figured out what drives the differentiation of these sublining fibroblasts. As shown in the middle of the slide, they found that endothelial cell-derived Notch ligands drive Notch signaling through Notch 3 to drive this fibroblast differentiation. This enabled them then to either knock out or block with monoclonal antibodies Notch 3 signaling, and it abrogated inflammatory arthritis in mouse models, as shown on the right, implicating that targeting fibroblasts may be a pathway for treating rheumatoid arthritis. Focusing further on fibroblasts, the exciting recent work highlights that it's the fibroblastic CTAP-F in the synovial CTAP that's associated with treatment non-response. Now, this comes out of a collaboration between the AMP and Cos Pitsalis. His clinical trial, shown at the top, the R4RA trial, took patients who were TNF receptor inadequate responders on the left and then treated them either with rituximab or tocilizumab. This led to the right to identifying patients that were not responsive to any of these drugs and are therefore classified as refractory. Well, now our clever computational biologists in the AMP, Nia Miller and Shomo Rishaudri, as shown in the lower left, used the AMP single-cell RNA-seq to generate pseudobulk RNA-seq, which they could then compare to the bulk RNA-seq from pretreatment biopsies from the Pitsalis trial above. This had allowed them then to assess treatment response from the trial based on the predicted CTAPs. And the striking finding was, as shown at the arrow, that it's the F-CTAP that was associated with non-response, strongly implicating the importance of fibroblasts in the unmet need in rheumatoid arthritis, namely treatment-unresponsive patients. In summary, we have been stratifying patients into CTAPs, cell type abundance phenotypes, based on the composition of their synovium. We think this is an important step forward in precision medicine for RA. Each CTAP is made up of distinct cell types and cell states and can predict treatment therapy. And looking at each CTAP, we can figure out which cells and pathways are dominating in that stratified population of patients. We're defining new pathogenic T-cell, B-cell, and macrophage cell types and cell states. I only highlighted a few along the way. And the role of inflammatory destructive fibroblasts, especially in their relevance to treatment inadequate responders. And finally, overall, we emphasize the essential role of synovial tissue interrogation in precision medicine and in deconstructing and reconstructing rheumatoid arthritis. And I highlight that this evening there will be posters presented by Fan Zhang, who defined the concept of CTAPs in this work, and she'll talk in more detail about them, and Kevin Wei, who is working in the new AMP-AIM and will highlight its focus on spatial transcriptomics as the next step in deconstructing and reconstructing rheumatoid arthritis. And with that, I'm happy to introduce Jill Byan, who will talk about lupus.
Michael is always a really hard act to follow, and I'm humbled and invigorated to represent the lupus team, so let the data begin. So as you've heard, there were two phases of AMP, rather phase 0, 1, and 2, and I also want to point out, in addition to the technical evaluations, we also hoped to provide insights into clinical management. So obviously, we needed first to find out whether getting tissue being the issue is in fact safe. And indeed, taking 15 sites who consented 475 patients to get a research biopsy during a clinically indicated biopsy, 449 patients, we were able to get tissue, and surprisingly, reassuringly, showed that the SAE rate was very, very low, with only 27 patients having probably related AEs, and only resulting in 17 serious events, 4 requiring a transfusion, with overall 3.8% related SAEs, very similar to that which we see in getting a typical standard of care biopsy. So phase 1 had two approaches. The first approach was plate-based transcriptomic analysis of the kidney immune cells. These were obtained from 24 lupus nephritis biopsies in 10 donors, and it was not agnostic, but rather focused on the immune cells by CD45 sorting. And there were 21 leukocyte clusters, and only 3 of these clusters were actually seen in the healthy donors. And that was resident macrophage, T effector cells, and the epithelial cells. So what did we learn from these immune cells? As shown on the top, we can see that the interferon response was elevated and correlated with blood. Cells expressed pro-inflammatory and inflammatory resolving responses. Local activation of B cells correlated with age-associated B cell signatures. There was evidence of progressive stages of monocyte differentiation, and specifically 2 chemokines, CXCR4 and CXCR1, were broadly expressed, implying a potentially central role in cell trafficking. Taking the other approach, which was agnostic and evaluating through a fluidigm-based transcriptomics, our group focused on isolated kidney parenchymal cells. And these were from 21 lupus nephritis patients and 3 controls. And you can see in then the Tisney map on the upper left that we were able to identify proximal distal tubular cells and the loop of Henle. And our main findings in this phase 1 were upregulated type 1 interferon signature was expressed in tubular cells and concomitant keratinocytes of unaffected skin in patients compared to controls. And these signatures, the high interferon and fibrotic signature in tubular cells, actually correlated with a non-response. And I'll show you a little more about that in a moment. Tubular cells from mixed class lupus nephritis had distinct expression profiles compared to membranous and proliferative. So 369 SLE patients with a UPCR greater than 1 consented for phase 2. Of these, 264 were eligible for follow-up at 3, 6, and 12 months. Of these, 180 are included in a responder outcome analysis I'll show you in a moment, and we utilized definitions of response which were concordant with those used in typical FDA pivotal studies. But one of the things we learned looking at all the data in aggregate was that the majority of patients with low levels of proteinuria actually had clinically actionable histology. And this supports to us as clinicians the importance of evaluating early disease, and we're going to be looking at that again at AMP1. But if you can see clearly on the left, with the UPCR less than 1, the majority of these patients had proliferative disease. And both low and high levels of proteinuria associated with increased activity and chronicity, suggesting that we may need to really lower the bar in evaluating for lupus nephritis. In this data set, about half of these patients presented only with lupus nephritis and no extra renal manifestation. These patients, by evaluating the PROMIS 29, tell us that they actually don't experience fatigue, pain, or impaired physical and social functioning compared to those with extrarenal disease, suggesting, again as clinicians, we have to carefully manage these patients despite any complaints. Now to evaluate the response outcome, this is showing you the demographics, baseline characteristics, and biopsy class of the patients. Importantly, these represented the patients we see. 42%, most were women, 42% were Black. They almost all had serologic activity. But interestingly, class 5 was seen in about 1/3 of the patients, again suggesting to our industry partners, let's pay attention to membranous. Now, how did the patients do? These are heat maps of the temporal patterns in the renal response. And the data are sobering. Only about 22 to 28% of patients actually achieved a complete remission. And it's hard a little bit to see here, but only 4% of the patients actually showed sustained remission. And so I think this is really, again, tells us we have a lot more to do. Now, what were the predictors of complete renal response? Having anti-DNA positivity at baseline, having a change in the UPCR by about 25% from 0 to week 12. Those were both predictors at 26 and 52 weeks. And at 52 weeks only, we add another parameter, and that is coming in with lower chronicity predicts a better response, not necessarily unexpected. We also had an opportunity to further evaluate our African American patients by looking at the APOL1 risk variance. And it was interesting that in this data set, the variance did not associate with class activity, chronicity, baseline serology, or response. But importantly, those Black patients with 2 risk variants clearly had a lower GFR at the end of the study. Now we can look at liquid biopsies, and this is the work championed by Andrea Fava, who will have a poster in this afternoon, that urine proteomics identified class. They provided biomarkers of lupus nephritis activity and tracked response. Interestingly, proliferative lupus nephritis was characterized by an upregulation of neutrophil and myeloid activity. And these markers, IL-16, which polarizes macrophages, CD163, an activation marker, and proteinase 3, coming from the azurophil granule of neutrophils, are urine proteins among the most highly correlated with histologic activity. But particularly exciting and applicable, again, to the clinicians, CD163 in the urine outperformed the change in proteinuria by 3 months in predicting who would respond to therapy. Turning now to the transcriptomics, and quickly, just to tell you, we used typical methodology with 10x, and you can see there were 155 renal biopsies, and already we're moving to 409,000 tubular cells to analyze. And some of the highlights: injury-associated macrophages increased with lupus nephritis activity, and they're enriched in class 5. And you can see this on the left. These population of injury-associated macrophages with the license plates, as I show, were highly associated with activity and seen most prominently in those with class 4. Now, interestingly, we also had an opportunity to look at the class 2 that didn't get into the pipeline, but in class 2, this is really interesting. These same injury-associated macrophages were also expanded. And these seem to associate with fibroblasts, again implying macrophage crosstalk with the fibroblasts. And just to tell you also, the chronicity index associates very negatively with cytotoxic T activity, cytotoxic T lymphocytes, both in the blood as well as the kidney. And you can see in the bottom graphs, the yellow, those are the patients with the most chronicity having the least number of these cytotoxic T cells. And this is a very exciting study that you will also see presented as the poster from Alice Horsberger and Deepak Rao, where they looked at the blood immunotyping, identifying distinct kidney histopathology and outcomes. And in this study, it was an unbiased evaluation, identified 3 immunologic groups in the blood, G0, which actually aligned more with the patients who didn't have lupus nephritis, and these were immunologically inactive patients with higher chronicity. G1, interestingly, the high interferon signature actually associated also with poor response, as we had shown earlier. And the G2, which are characterized by the cytotoxic T cells, these associated with the highest complete response. So where are we going in AIM? Well, we're looking at patients with very low levels of proteinuria. This is a chart telling you how we're doing, but already with 10 patients with proteinuria below thresholds we might consider to be important, 60% have actionable lupus nephritis, and all of these are available for our transcriptomic analysis. And finally, moving to spatial transcriptomics, where are we? We have analyzed, evaluated by mapping through AMP onto the spatial transcriptomics. Excitingly, this represented as a patient who had class 2 that progressed to 5, that progressed to 4-5, and the arrows are pointing to pathways between NK cells and CD4 and CD8 cells. And as one progresses, these networks are actually increasing. So I'd like to thank you all for listening to us today and to really appreciate the work of the clinical network that so well integrates with science. And I love that quote, "About us requires all of us." Thank you.
Good morning, I'm Carolyn Szybalski, and I'm delighted to introduce the Sjogren's team and the milestone that we've accomplished to date. So I'll start by introducing my co-PIs, Doris Ferris, Alan Baer and Blake Warner. We have 5 clinical sites that are currently enrolling participants and about to add a 6th as we are collaborating with our colleagues at NYU from the SLE team. We have great expertise in rheumatology, ophthalmology, and oral medicine being present at each of the clinical sites. And in addition, expertise in computational biology with Chris Lessard, Blake Warner, and Jimmy Yee. We also have our patient perspective through the Sjogren's Foundation, and very thankful to have Kathy Hammett at the table. So having completed planning and pilot phases, we're about to embark in the scale-up phase to better understand the phenotypic and molecular heterogeneity of Sjogren's disease, the mechanisms inherent to progression, and to the molecular overlap between Sjogren's disease and its cousin SLE. And all this to identify therapeutic targets, since to date there still is no effective treatment for Sjogren's. So the 5-year scientific agenda, which we developed during the planning phase, has 3 components. First, the prediction of Sjogren's disease development and progression. Second, aim pertains to the elucidation of Sjogren's disease, molecular and phenotypic heterogeneity using multi-omic data, and we will explore the associations between molecular covariates of Sjogren's disease and phenotypic features of disease activity and damage. And finally, we'll be looking at determinants of glandular tropism by comparing Rho-positive Sjogren's disease participants with Rho-positive participants with SLE, and looking at various determinants. So while the STAMP study is cross-sectional, it has a longitudinal component since we'll be recalling participants that were previously participating in the NIDCR-supported SICA project and the NIAM-supported OMRF cohorts. And this was 10 to 18 years ago. So a unique opportunity to call back these participants, and we will call 185 of such participants. We will also recruit, or we are recruiting, 300 new participants with signs and symptoms suggestive of Sjogren's disease, and we expect that about 40% of those will meet the classification criteria once we've worked them up. We have a small group at NYU and expect about 20 of the Sjogren's disease SLE cohort overlap, and then a number of healthy controls, mainly recruited at NIDCR. So this is a gamut of tests that we are conducting in the 3 main domains of the disease: oral, ocular, and rheumatologic. And down the blue box on the right, the list of specimens that we are collecting so we can apply the cutting-edge technologies. So we have completed 4 pilots. First pilot mainly focused on operations, and we've finalized, tested our SOPs, CRFs, operations manuals, trained and calibrated our clinicians. And then we had 3 pilots that were tissue-focused, where we compared various protocols for cryopreservation, dissociation, and fixation of label salivary glands, as well as spatial platforms, and also investigated the feasibility of using new 10x genomics technology to assess historical FFPE-preserved label salivary glands from SICA and OMRF. So to date, we have enrolled 84 participants, and given that we started recruitment in late June, we're confident that we will be reaching our target of 568 participants by the end of year 4. And most impressively, Chris Lessard and Blake Warner, working with members from the other AMP-AIM cores, have completed the 3 tissue-focused pilots. And you will find out all the details about which technologies, cutting-edge technologies, have been selected for AMP-AIM, or for STAMP, by visiting Chris's poster tonight. So please do, and prepare to be dazzled by this beautiful poster. So I'd like to thank, obviously, our funding partners from NIDCR, NIAMS, and NEI, our industry partners, and also our Sjogren's Foundation, with the patient's perspective being at the table, and of course all my colleagues from AMP-AIM. Thank you. And I'd like to introducing Jose Scher.
All right, thank you very much. Good morning, all. Privileged to be able to represent AIM, psoriatic disease team, with the ultimate goal to elucidate the landscape of immunoendotypes in psoriasis and psoriatic arthritis. We're called LIPS. We are a diverse and highly collaborative team of physician scientists, mainly from the dermatology and rheumatology spaces, but we're also very proud to count within our steering committee with 4 patient research partners that help us guide our science and what can be done for our patients. So the problem at hand is how to tackle the better understanding of psoriatic diseases, particularly in terms of pathogenesis. And the reason for why this is important is because psoriasis is one of the most common immune-mediated inflammatory skin diseases. It affects 3% of the population. That's about 12 million psoriasis patients in the United States alone. Psoriatic arthritis is a common form of inflammatory arthritis that occurs in about 1/3 of patients with pre-existing psoriasis. It's characterized by joint pain, swelling, deformity that leads to high morbidity and mortality. Uniquely, however, there is a passage, a window of opportunity to study this transition from skin inflammation into psoriatic arthritis, which now lead us to a better understanding of immunoendotypes of both psoriasis and psoriatic arthritis, but also to try and discover potential diagnostics and therapeutics during that transition window. And so within ELIPS, we have 3 fundamental questions. We've assembled 3 different cohorts to answer the following aspects of the disease. Number 1, are there any key immune and effector cells in either the skin and or the joints that promote these specific phenotypes at disease onset? Number 2 is the question of whether or not we can define both cellular and molecular signatures of particularly treatment response. There are many patients that respond to certain drugs and not to the others. Is there anything we can learn from spatial and single-cell technologies? And number 3 is the idea that we can look at both host and environmental factors, particularly microbial, that may contribute to this transition or passage from skin disease into synovial enthesial inflammation. So we're using novel and innovative methods to try and discover new targets in psoriatic disease. In the skin, we obtain biopsies and skin swabs to perform spatial transcriptomics and skin microbiomics. In the peripheral blood, we are pursuing site-seq and other single-cell RNA-seq methodologies. And from the synovium, both single-cell and spatial transcriptomics to try and reconstruct disease states. Now, we're also trying to bring innovation to attempt to improve clinical care as well. This is nanoarthroscopy to enhance synovial sampling, the way we go into the joint space. And we're using this first medical-grade single-use chip-on-tip nanoscope system. It combines the latest technology in imaging within a imaging sensor of a 1 millimeter radio with nanoarthroscopy instrumentation. It's designed for more precise atraumatic insertion into joint spaces for more efficient resection of synovial tissue under local anesthesia. And this is what it looks like. Let's see if this works. Praying, excellent. So patients under local anesthesia is in the office and gets both a camera that goes in and an instrument that now selects the right type of tissue. So now we can process it and use it for the specific scientific outcomes that ELIPS is looking into. And one of the, great, this is working now. I was praying that the video worked. One of the early wins for ELIPS is this idea that we can reconstruct spatial transcriptomics both in healthy and inflamed skin. And already we're looking at potential targets that may govern disease pathogenesis, particularly HIF-1 alpha signaling pathway, as it pertains to downstream activation of Th17 and IL-23/17 cytokine production. And with that, I'd like to thank the FNIH, the NIH, the partners, and our patients for the work they're putting in. Thank you.
Hello, and good morning. My name's Mark Levesque, and I come to you from Merck, and so I'm here to give you a perspective from industry side of things on how we translate what you all do into making new medicines. I thought a lot about the early inception of this program, and thought a lot about how grateful I am to the folks who got it started. In particular, I want to mention Lisa Olson's name, since she was a big part of actually getting this off the ground and was a real champion from the industry side of things. I come to this as a physician scientist, and so I have this drive and desire for us to actually make medicines. And so one of the things that I think about a lot is what are the features of AMP that we can drive into what we do, and how can we turn that into medicines? And I start with basic science, and I think this kind of gets a little overlooked, at least within industry. We do a lot of this kind of work. And so I point out Vanessa Peterson. She was one of the early adopters of the site-seek type of techniques. She developed something called REAP-seq, but it's very similar in nature. But this technique spurred a lot of success within our company in terms of being able to interrogate tissues ourselves. And we learned from AMP how to do this. And what that success breeds in a lot of ways is the ability to do more work internally and to actually complement what it is that you all do. And as an example, her group has developed drug-seek techniques, spatial transcriptomics, and optical pooled screening techniques that are part of our everyday work process. And so I don't want to overlook the idea that a lot of this kind of work also permeates what we do. The other way I think a lot about how we use the data from AMP is that we use it for new drug discovery. And I think this is what probably comes first and foremost to everybody's mind. And one of the things I want to point out is the work that's in the upper left part of the slide there about inflammatory fibroblasts. This is from a review article that Kevin Way and Michael Brenner wrote, and Michael talked a little bit about this a few moments ago. This has come into our way of thinking about how to treat disease, how to get at the unmet need that patients experience, because we aren't currently able in diseases like rheumatoid arthritis to fully treat patients. And so I think about how do we make inflammatory fibroblasts part of our work process, and actually a pretty good section of my group, about a fifth, is actually devoted to what I call stromal biology, just because of this work that Michael and Kevin and others have brought forward. And the example down there on the lower left on the bottom is it's a target that we're working on, and it maps to those inflammatory fibroblasts that he spoke about a few moments ago. And then likewise, he talked about inflammatory macrophages, and so that also translates for us into using AMP data to focus in on target populations. In this particular case, the example I'm showing is of IL-1 beta pro-inflammatory macrophages. And I just want to highlight the role that Nidhi and Handan played in this process. And then the last example that I want to talk about is the other way this permeates into what we do is that a lot of times we aren't sure when we identify these pathways what the best disease is to start with, and where is actually interdicting in this particular pathway going to have the most impact. And so I think many of you are aware that there's been a lot of data published about the use of low-dose IL-2 for the treatment of autoimmune diseases. And so pharmaceuticals went ahead and developed longer-acting versions of IL-2 called IL-2 muteins. And one of the areas that we were interested in figuring out is where should we put that first. And so we used the AMP data to actually decide, for example, that lupus would be a good place to put it first, because there were abnormalities in Treg populations that were present there, and it was the AMP data basically that informs how we go about doing this.
So hopefully I've been able to kind of give you at least a little snapshot about how we think about the AMP work, and there are many more examples within the company. We use this on the data on almost a daily basis to inform what we do. So once again, I'm grateful for the opportunity to speak with you and appreciate all the work that everybody's doing in the program. Thank you.
Thank you, Mark. I'm Rab Pringer from GSK, leading the Immunology Research Unit. If I could have the next slide, please. Okay. This one? Thank you. So I asked across the organization how and where are we using AMP data, particularly from our ASLE and more recently from AIM. And it became apparent that actually our scientists are very routinely using this data, have tried to capture in numbers some of the areas where we're seeing that impact. And we've heard today about how GWAS gives us long lists of targets, and for us to be able to have that disease-specific cellular level data is very informative. And over 200 targets we've evaluated in the context of that data, try and understand where they're expressed, where they're misexpressed, and what that might mean for a potential therapeutic. That data has then actually informed 16 targets, which we've then been able to progress into the next phase of drug discovery. We've also used it when we've got similar targets on the same pathway that are associated with disease pathology, but we want to understand which of those have got the highest potential, the highest expansion opportunity, and 3 targets have actually been able to prioritize out of that list to select them over others with similar pharmacological profiles. We've also used it to launch whole new target ID concepts and efforts to think about how we do functional genomics in a particular area, how we think about actually applying that to prioritize and decide which phenotypes we want to focus on. But having all of that data and internalizing it, as we've heard earlier, actually generates an enormous opportunity, but a real challenge. And so our computational biology group has actually built a single-cell visualizer, an analytics platform, and that's allowed us to generate 5 different ways that we can actually start to integrate that data and use it in the context of compound data, expression data, and genetics data to start to really increase the power and the impact of that. And then in the pink box at the right-hand side, there's actually many examples, and I've shown 6+ there, where we can actually look at the enrichment of genetics as a function of cell type, and that's allowed us to really inform the disease strategy, to provide new insights in terms of the types of cell types that we might want to think about addressing and characterizing more broadly. And good then to see the correlation between circulating cells, cells in tissue, and start to get insights in, are they genuinely enriched for that genetic signal, and therefore what might be the magnitude of the pharmacological and therapeutic benefit. And those numbers, I hope, illustrate that AMP RASLE, AMP AIM, and the data in industry context actually has had a profound impact on our ability to think about targets. It's had an impact on technologies. It's having an impact on the therapeutics that we prioritize and progress. But it's also allowed us to give us opportunities to much of our young talent in the organization to learn, to develop, and think about how we can use these types of data to help us develop medicines of the future. So just to finish with saying a huge thank you to Francis and the team for thinking about AMP, to allow us to bring together patients, pharma, and the technology developers and the academics to help us move forward with medicines of the future. So thank you, AMP, and thank you to the RASLE team and the AIM team.
I'll let you introduce yourself.
Okay. So I'm Mary Collins, representing the Lupus Research Alliance, a patient advocacy organization, and speaking to the patient voice. So I want to start by just recognizing the amazing contributions that patients have made to the AMP-RASLE and AIM studies. As mentioned, 475 SLE patients consented for kidney biopsies in AMP-RASLE through phase 2. And over 200 RA and OA patients consented for either synovial biopsies, arthroplasty, or synovectomy tissue samples through phase 2. And many of these RA and SLE patients also donated blood and urine samples to AMP-RASLE. And I might add, all these patients also donated their personal clinical information as well. And to date, over 100 tissue samples have been donated by patients across AMP-AIM, along with matched blood samples, and recruitment is ongoing. So this is an amazing contribution. And so we wondered what inspires patients to contribute to medical research. And so we asked our patient advocacy organizations for information about this, and also leveraged their websites. Some advocacy organizations actually support studies to look into this question. And in summary, patients highlighted two primary reasons that they chose to participate in research or clinical trial studies. And first of all, they highly valued the input from their physicians in providing both background information and in helping them to make their decision to participate. So the doctor's voice is very important for patients. But interestingly, patients also really wanted to contribute to research to find a cure and to help other patients who might also be afflicted with their disease. And I just highlight two quotes from web pages from patient advocacy organizations, one from the Lupus Foundation of America, where a patient saying, "I joined a study because I want my experiences to help move lupus research forward. It's going to take all of us to defeat lupus." And another study on the LRA webpage, "Trials are so important to understanding what it's like to live with lupus. Current treatments work to an extent, but there's still so much out there that isn't being researched. Without clinical trials, we wouldn't have therapies that can help better manage our lupus. We need more people to participate to make it better for you, for me, for everyone." And so I ask you, are we effectively communicating AMP study findings back to our participating patients? And I wanted to highlight that web pages for patient advocacy organizations can be a major source of information for patients. And we can include summaries of AMP study outcomes on these web pages. And I highlight excerpts from the LRA website, bringing patients up to date on what's actually been happening in AMP. And this includes both milestones in the AMP program, as well as highlights at research conferences that are summarized on these web pages. And then finally, I just want to ask the question, how can we do better in communicating to patients? And I encourage folks to partner with the advocacy organizations to enhance the information on their websites about AMP research, studies, and clinical trials. And things that can be done would include patient testimonial videos on their experiences in these studies, summaries of research or trial results, emphasizing the advances that have been made. Patients want to know that they have done something for research, and also what impact this might have on patients. We can share videos that summarize conference highlights of presentations from the AMP program. and of course links to scientific publications for patients who want the details. And then a question to think about perhaps is whether individual patient information resulting from these studies could actually be shared back to patients. And as aspects of disease heterogeneity in response to therapy are uncovered, can patients find out how this might affect them personally? So congratulations to the entire AMP, RA, SLE, and AIM teams, and especially to our patients. Thank you.
So thank you very much. It looks like we have 5 minutes for questions. We're also headed to lunch, and so you can catch us. And there's a lot of other people who are here from AMP, RA, Lupus, AMP, AIM. Oh, here we have a question. We'll start over here.
Okay, great. Hi, Will Chutko from Novartis, and I also am participating with the heart failure AMP that you hear about tomorrow. A comment and a question. Ours is a more nascent effort. First of all, this is a wonderful roadmap for us. We are employing the same tactics, so it's really gratifying to see the progress you're making, and particularly to the industry partners that have already attested to the impact that it's making in target selection and also patient indication mapping. So the question is for Jill. You've gone through the process now of taking biopsies from patients, and I'm sorry if I missed this, but I understood that the indication for the kidney biopsies was there was a clinical indication and it was in a research biopsy.
Yes.
We're struggling with this question about, in our efforts similar to this, is the control. How have you addressed this, and what strategies have you employed for the healthy control population that would be great to map against these disease patients?
So for this study, we used healthy donors for kidney transplants. That was actually the control tissue, and that was considered a non-invasive situation, and that's what we did. So it was relatively easy in centers that do the transplants to obtain that tissue. Now, whether it's exactly comparable to a research core that you get in a clinically indicated biopsy, not so, because you get more tissue the other way. But I was really pleased at the safety and how willing patients were to actually contribute these research cores. Very few denied, actually, and again, few complications.
Fantastic presentations. Judith, over the past 2 years, we started a dialogue across Foundation NIH-funded initiatives. In our case, we lead the Metabolomics Initiative for Alzheimer's. In looking at some of your diseases of interest, we realize how much there is in common. Metabolism is key, vital, important for inflammation, immune dysregulation. So I hope we can find more ways as we debate over the next 2 days to enforce this cross-hybridization where we can leverage big data, whether metabolism data, gut microbiome data, and much more to teach us about a lot that is common across diseases.
So I agree completely, and you showed us beautiful data in AD that we are not getting a lot of metabolomics or lipidomics. We have one of our LSPs, Leadership Scholar Program, who is doing some lipidomics, but we would love to talk to you about this.
Hi, Mary Wheatley with National Scleroderma Foundation. My question actually kind of builds on the last comment, but each of you are experts in your field, of course, and kind of drill down into specific disease states, but also by nature of the work you do, know a lot about, rheumatology, immunology, and dermatology across these fields. What work are you doing to kind of look at the learnings across autoimmune diseases now as we think about kind of the next phase of AMP-AIM?
So I'm not sure who is going to take that question. So Barry, we think that's a great question. We are looking at skin now in 2 different autoimmune diseases. There's some work we've actually talked to the investigative team that is working on a P50 that's involved in scleroderma. And so I've talked to them about sharing protocols and sharing different methods, but maybe Bob was going to pull me out of this hole.
Well, I think you did pretty well. You probably hear a lot more tomorrow on the data thing, but the systems biology inflammation is an approved concept now within AMP, and a protocol is being developed, and it is to look at inflammation across diseases. And just to say it quickly, the commonalities between diseases are astounding. I mean, the changes in monocytes in the blood that you saw in AD, I'm sure you'll see comparable ones, they see similar changes in type 2 diabetes, for example. So And the flip side is that we do see this heterogeneity within patients with the same diagnosis. So I think we really need to transform the way we do medicine, the way we think about patients, where we think about the clinical diagnosis because that's the patient, but you also have to get to the mechanism to understand how to treat effectively. But stay tuned, and it is something I'm going to take the floor for quickly to plug that the different amps are going to have to come together to make this work. And that's not a given, but I think we do all share that concern that we've got to learn about going across diseases.
Okay, we'll start over here, and these will be our last 3 questions.
Thank you, Virginia Savova-Sanofi. It's been a really exciting morning. So happy to see all the progress is put together in such a nice overview. This is a question on lupus nephritis, mostly to Jill, but perhaps our industry colleagues could also jump in. The feedback from the clinical teams has been that it's very difficult to position a molecule in lupus nephritis because it's hard to recruit patients, it's a rare population, fewer. What do you think is the implication of observing these patients with UPCR less than 1 but actionable? Does that mean will that create a new opportunity to actually target this indication? And what are we going to do going forward to make this more palatable to clinical teams?
My answer is yes, yes, and yes. I think as we understand disease, prevention is probably the most important aspect of what we do. What are those protective mechanisms that fell apart? And I think that's what we're going to see in class 2. And we're going to see that in those that have UPCR that are low, yet these patients are often serologically active. And I think this is an unprecedented opportunity to embrace that, quite frankly. And when we find factors in the more advanced disease and we go back and look at these early diseases, it might not be too late. There might not be chronicity. There might not be all that macrophage fibroblast crosstalk. So I'm optimistic. And patients are accepting this.
So I'm Gil Oman from University of Michigan. I'm a member of the FNIH board and delighted to see this in-depth two-day meeting. I have a daughter with psoriatic arthritis. And she's benefited greatly by drugs available. It goes back 35 years. She started on Enbrel. She's been on a whole series of other drugs. I want to ask you whether anybody is addressing the subject of longitudinal features of the disease and longitudinal response to the same drug that seems to work well and then becomes less effective. And it seems like it's mostly trial and error after that observation.
I'll take that one. Our second cohort specifically is designed to look at treatment response longitudinally, both at baseline and perhaps after our participants have failed a second or third biologic. And so that's critical. We know, particularly in psoriatic disease, specifically in psoriatic arthritis, that the first biologic is critical to the success of the outcome down the road. So we are addressing it with that specific cohort.
Thank you.
I can jump in too, and from an industry perspective, one of the interesting things to me is the time sequence of our diseases and how the right drug at a particular moment in time can be different for patients. And so we are actively thinking quite a lot about that. And I think a little bit related to Virginia's question a moment ago is the earlier we can intervene, the better. There's almost a reluctance, not so much on industry's part, it's almost societal in some ways about how we attack very early disease. And I think we should consider being aggressive, but that also carries with it risk. But it may prevent some of those long-term problems that people get into because we're not aggressive enough early on. And so I do think that's a paradigm that has to work its way through our community.
If I may add 30 seconds, we are running a study on preventing psoriatic arthritis in psoriasis patients. Yeah. And that's helpful. It's been done in lupus. It's being conducted in rheumatoid arthritis as well. So that addresses that question of prevention as well.
Jeffrey Siegel, FDA. Thank you very much for the whole panel. Really fantastic presentations. I have a question. I think it's directed mostly at to Mike Brenner and to Jill Byan. Back in the old days, before we could interrogate these diseases at the cellular and molecular level, we relied on animal models to give us insight into disease mechanisms. Do animal models play any role in following up on the insights that we have, that you've produced, or are the animals really working on a totally different mechanism than human disease?
So of course there are always two sides to the story, and I can argue both sides because I've been on both sides. So I think what's evolved is that we used to look to animal models to predict what the human disease is, and I think we increasingly recognize this is not the case. On the other hand, when we identify a fibroblast or a macrophage or a T cell, animal models can be very effective at asking, if you target that cell or that pathway, does it affect the inflammatory process? It may or may not work in the disease, but it's a validation that it can be therapeutically targeted. And so we tend now to make discovery in humans, all the single cell and high dimensional data. And then what we find there, go back into mouse models to test therapeutic effects in inflammatory states, rather than see the model as a model of the human disease. And work in lupus by Neerha Cohen and Paul Hoover have taken the lupus models, now that we have both the human lupus single cell that Jill described, and then doing the animal single cell analyses, they can predict which models are good for the macrophages in the human lupus, which are better for the B cells, and essentially appreciate how each model has value and relevance, but none of them reflect the human disease.
I agree. I mean, I think we were always going forward, and now maybe we're going back. And I think that makes a lot of sense. It's about context also. And I think trying to create the context in which something has been observed in a human into the mouse would be very effective, and exactly what Paul Hoover and Neerha Cohen are actually evaluating now. Those inflammatory macrophages, really drilling down on, we haven't discussed functionality, like what's the function of these expressed genes? When a cell expresses this, what does it really do? And I think we can address some of that in a mouse model as long as we have the context correctly.
Thank you.
Courtney.
All right. Thank you so much for this incredible panel. Really appreciate all of your perspectives.